Welcome to Deep Learning Explainer. Today we're going to look at model-agnostic meta-learning. It's a way they lay your model to adapt a new tasks very fast. And it's actually inspired by human learning because we don't really need a lot of training examples to perform new tasks. They are not too different from the original tasks. Okay, let me show you an example, a scenario that you can use, how you will use this algorithm. So let's say you are doing image classification. You have a model. They classify these four classes, which are cat, dog, lion, and apple. Then you already train this model, but just one day, for some reasons, you need to include two more classes, which are orange and a bike. And the traditional way is you really need to have to label a lot of orange images. They belong to orange class, and also a lot of images they belong to bike class. Then you retrain your model, combine these four classes images. Then you retrain your model, but the problem is you need a lot of data for those two new classes. It's not really efficient, so that's where these meta-learning algorithms come in. It basically want you to use as little new data as possible to adapt these new two classes, orange and the bike. By the way, I make deep learning explained video every week, so if you would like to receive more relevant videos like these, don't forget to subscribe, and your subscription is also my best encouragement to make more videos like this. Yeah, and this work is done by Chelsea, Peter, Sergi. So in order to discuss the meta-learning, we must talk about human intelligence, because meta-learning is actually inspired by human learning. So what are the properties of human learning, human intelligence? The first one is a human can recognize the objects from just a few examples. It's very straightforward. Even you never seen that kind of class of images before, I just need to show you one image, a few images, or even one image. Then you can recognize that kind of things in the future. Maybe I give you a handwriting. Maybe it's like this. So what is this? Maybe this means 1 and this means 2. And in the future, every time you see this one, you will just say it's 1 and this is 2, right? But for computers, usually for deep learning models, it's usually harder. Deep learning model requires a lot more data points to learn things, so it's not that efficient. So that's why recently a lot of machine learning research focus is like how to make the deep learning model more efficient, and the meta learning is one of the candidates. Okay, so another property of human experience also we learn new skills after just a few minutes of experience. Yeah, which is true. Like reinforcement problem, reinforcement learning, the traditional reinforcement learning algorithms maybe takes 100,000 times of trying then in order to learn how to drive the car. But as humans, you don't really need that to try that many times, then you know how to drive the car. So these are a few properties there of human learning. And the goal of meta-learning, model-agnostic meta-learning, is to firstly find the core concept is to find the parameters they are easy to adapt for new tasks. You can see it's a little bit like the pre-training thing. When we pre-train language models, like BERT, we train a very good representation of the text of your target languages. Then after that, you fine-tune your BERT model on the downstream task. It can relatively fast to adapt those downstream tasks. So the author Chelsea also mentioned is actually she got inspired by the pre-training thing. And this meta learning method is a little bit different from the concept is also similar to pre-training, but a little different from what we are familiar with, like language model pre-training. It's actually use a label data to do the meta learning, or you say it's use label data to do pre-training to find the best parameters they can adapt a task really fast. This is a core concept. And also you also have another requirements to use the small number of gradient updates. Basically use only one gradient updates or just a few. So that means the model will need to learn very fast. If you can only perform the gradient updates for a few times. And this is the illustration of this algorithm, model-agnostic meta-learning. So we can see the gray line here, here and here are the learning adaptations, and 1, 2, 3 represent different tasks. So we have 3 different tasks. Then we want to find the parameters. Theta is a parameter here. So you want to find a point where it's close, it's distant to theta 1. Theta 1 is the more ideal point to perform the task 1. And the theta 2 and the theta 3. You want to find a point that's the distance between this point and these 3 points are closest. So that when you do the adaptation in the future, it's very easy to adapt. You just need to do a very small step, then you can achieve the ideal parameters. And same goes to the theta 2, same goes to theta 3. So this is the point this meta-learning algorithm want to go to. And they say if you can find these parameters, you just need to fine-tune a little bit to perform very well in the task 1, task 2, or task 3. So this is the whole concept of that. And how to go to these ideal points from the randomly general parameters theta. It's actually straightforward. You need to calculate the gradient for each task. Then you combine or you sum up all the gradients to each task. So let's say we perform one learning. It's just a general learning, which is to task 1. We have one loss function for task 1. Then we do the gradient. Normally we do the gradient, right? We do the gradient to the loss function with respect to theta. Then we got this one. Then we got this gradient, right? But if you only have this gradient, then you update toward this direction. It's not ideal. It's still very far away from theta 3 and the theta 2. Then it's not good for that. It's only good for theta 1, for task 1. But these parameters will be very, very bad for adapting task 2 and task 3. So what if you plus the gradient that you got from the task 2, which is to do the derivative to a loss function 2 with respect to theta, and you also do the gradient to L3, then you sum them up. So you have 3 vectors now. If you sum them up, you can see their vector sum is here. So you will know, oh, this direction, going to this direction is the most optimal for adapting these 3 tasks in the future. Then you find out the direction here, which is these 3. This is a direction only. Then how much step you should go is basically depending on the learning rate, beta. So in order to find out this ideal point, you need to do the learning, which is the traditional way of calculating gradient to each task. Then you sum up all of the gradient. Then you find out which direction you should go to in terms of make it more easy to adapt for these 3 tasks. Basically, you sum them up, then you do your gradient descent with your learning rate beta, then solve the problem. So I want to formalize this. There are 2 steps. The first step is just learning. We call it learning. And second step is called meta-learning. And we will have 2 different kind of data set. First is de-training. This is just for the learning for this step 1. And we'll have another data set called de-validation. And this validation data set is very confusing. I don't think it's a good name. But this validation, say, you can call support data set, is actually to perform meta-learning. It's not validate your model performance. It's actually to do second stage learning. So it's, or you can call support data set. This set, it's not to evaluate your model. It's to perform second learning. So we do the first learning here, which is traditional machine learning way. You do the gradient to loss function to the task I, to the task I. Let's say we have 3 tasks total. I equals 1, equals 2, equals to 3. Then we use this randomly generated theta. Then we perform one gradient update. We get theta I, right? Then this is the theta I. Then we get theta 1, theta 2, theta 3. This is ideal. And a little bit different from the previous picture I showed you. Previous picture, we just want to get a gradient to a loss function 1, loss function 2. But in this specific algorithm, we actually want to get theta I, and the next you understand why we want theta I, because we want theta I. We want to use theta I to calculate gradient. We previously I told you, like, we want to get the gradient of loss function I 1 and loss function 2, loss function 3. But what parameter we need to put in? We actually don't want to put a randomly generated parameter. We want to do at least one gradient update to that. So it's like a little bit more fine-tune the parameters. Then we put that here. So it's more accurate. Then this gradient is more meaningful. Then we will have in the case I show you, example I show you, we have 3 gradients. Then we sum all 3 gradients up. Then because this gradient is just the direction, so we will have to the multiplication to a learning rate beta. Then we can have a new gradient. And to be aware of this theta, we don't use theta 1, theta 2, theta 3. We don't use that those like slightly updated theta. We use original theta, which is randomly generated theta, but with the direction, the right direction, ideal direction. Then basically this is what you get. You get theta I. So theta I is the ideal point, which is here. So originally you got theta. Then we use the step one, which I show you already, to calculate these 3 gradients. Then we sum those 3 gradients up. Then we perform gradient descent. Then we update to theta I. Then theta I is the ideal point, the ideal parameters that you can adapt for these 3 tasks very easily. So this is the algorithm. Okay, I know maybe a little bit confusing, so you probably want to repeat these videos for a few times and also checking out this paper, original paper. Okay, so combined, we have this algorithm. We have original randomly generated theta. Then we calculate the gradient of loss function I. Then we perform one gradient descent, one gradient update. We get a theta I. Then what's the purpose of getting this theta I? This theta I is basically to calculate the real gradient that we want in the end. So we have I gradients. Let's say we have n task. We have n gradients in the formal example, we have 3 n equals 3, so we sum all gradients up. We have the eventual gradient that we want, the eventual direction we want to go to. Then, yeah, we have our learning rate, so we can update our theta. Yeah, then we get theta I. Okay, so have you found a catch? The catch is this: if we do the gradient back propagation, we need to do back propagation through gradient twice. So the first one is gradient here, and these things actually have the gradient related to this one. So it's a little bit tricky and it's computationally expensive. So that's why they also propose one first order approximation, which is only use one gradient update. And the result I will show you later is not much different from doing 2 gradients. Okay. So if we write this down in the more algorithmic way, you can see this. We have the distribution of a task. So it's basically your data. Then we have two kind of data. One kind of data is here, training data, right? Then this is validation data. Then we basically evaluate. We found a gradient to the loss function I with respect to k example. This is we call k-shot learning. Previously I didn't mention how many examples we have in their setup. They have k examples, and you perform the gradients on these k examples. This k is like your, maybe I will say it's your batch size. It's your batch size. You do gradients only one time to this k example. This k example is 100. Then in this batch, it's not like your batch size, just like the whole data set you want to perform on. How many that you have, then you just run a gradient on all of them. Okay, so if effectively it's like your batch size. Okay, you just do one batch. In one batch, you just do one time update, and one time update, the whole batch of data points is 100. It's k. Okay, so you only do one time for one task. One time, one task. So if you have 3 tasks, you only do three gradients. Calculate 3 gradients, and you have 3 different theta. Okay, then you got theta I, theta point I. Then what does this mean? This is actually to calculate another gradient here. Then you sum all these gradients up. Then you perform another gradient update. You got your theta. This theta is the one you really want. And depending on how many gradient updates you want, this is called one gradient update. Later they will use this matrix in their experiment to see how many gradient updates you need to perform. But no matter how many times you update, you only have k data points each task. Okay, and they actually perform this on the regression, reinforcement learning. But in this video, I only want to focus on the classification problem, because this video is just I'm just laying out the groundwork for the next video. Next video will be the lifetime learning for language. And in order to understand that paper, we need to understand this paper first. So, and the classification is the main part of that. So I only want to look at the classification. Let's look at the data sets they use for experiments. So the first data set they use is Omniglot, which contains 1623 different characters from 50 alphabets, means from 50 different writing systems. You can say that. And another is like MiniImagenet. It's a subset of ImageNet, and it contains 64 training classes for training, and 12 validation classes, which is used for meta-learning, and 24 test classes for held out data set. Okay, so this is the setup. And as you can see that in their first experiment, Omniglot, if it's 5-way accuracy, it means there are 5 different classes being input to the model in the test time, and the one-shot in the one-shot learning setup. One-shot learning setup means in meta learning time, in the learning time, they only can see one example at a time. Yeah, and one thing worth paying attention is this test in the test time, because those also are new classes in the test time, so you still need to learn in the test time. This is what I assume. Otherwise, how the model can figure out those classes are. So this one shot can mean in the training time, also can be can mean like in the test time. So this is a little bit confusing to me. I'm not really sure this one shot learning means meta learning time, learning and the meta learning time over test time, but I just assume they use that for both learning time and the test time. But anyway, you can see in the 5-way accuracies, not much different from the previous state of the art, but it's slightly better than that. But because those accuracies are just for most of the methods, they can achieve very high accuracy. So you cannot see a difference. Even the algorithms wise difference is very big, because the task is somehow too easy. Let's look at a slightly more difficult task, 20-way accuracy. And you can see the difference is larger, at least like this from the previous state of the art. In the one-shot learning setup is 0.8%, which is still not significant. And the 5-shot learning is just 0.3% better than the previous state of the art. Still not significant. We probably haven't been convinced that yet. But in the MiniImagenet, you can see in the one-shot learning, test time one-shot learning, the proposed methods actually outperform the previous state of the art by 5% accuracy, which is big. And for the 5-shot learning, which you learn more, so accuracy is apparently higher, and the accuracy compared to the previous state of the art is 3% higher. I think that's a lot. That's a lot. So it convinces us that model-agnostic meta-learning is somehow quite good. And remember this picture I showed you in the beginning of this video. So now you know how to do that. You apply this model-agnostic meta-learning algorithms. Basically, you train on these 4 classes first, but you do the meta-learning. You do the standard training and the meta-learning. So you do the 2-stage gradient update. Then after that, in the future, when you need to add these 2 new classes, your model can just perform the regular learning and adopt these 2 new classes relatively fast compared to you using just traditional supervised learning. Yeah, so that's all for today. So give it a like and don't forget to subscribe for more relevant deep learning videos like this. And other than that, take care. Until next time.